me see. Oh, perfect. Okay. Good day to you, everyone. Again, we see each other. We're going to pick up the pace a little bit to finish up with the vector calculus stuff. Last time we talked a lot about divergence and gradients, etc. We're going to talk about a couple more operations and just get all the tools under our belt so that we can start actually studying fluid mechanics. The next thing I want to talk about is the curl of a vector field. Curl of a vector field. Okay, so if you think about vector to vector operations, we looked at the scalar product and the vector product. So we had the A dot B, right? So A dot B, and then we had the A cross B, right? Now, with vector calculus, we said the nabla operator is very important. So we already did the nabla dot U. Now we're going to do the nabla cross U. So that's called curl, also spelled like this, curl of U, okay? And again, if you think of nabla as a vector, it simplifies everything. So the same way we interpreted A cross B, you can interpret nabla cross vector U, okay? And it does the same thing, follows the right-hand rule, and it results in a vector that points in the direction of your right-hand thumb, right? So if you're rotating, in this case, from nabla to U, you're going to get the vector into the plane. And in this case, if you had nabla and U over here, you're going to get a vector out of the plane, okay? Of U and nabla cross U. But what does this operation mean? With the cross product, you had two well-defined vectors, right? And there was no differential change, okay? Remember, however, although we describe nabla as a vector, just to kind of simplify our thinking about it, nabla has derivatives in it. So it describes rates of change on top of its cross product with the velocity, okay? So the definition of the nabla cross U follows the similar approach we did with just the standard cross product. Okay, we had, except now we have d by dx, d by dy, and d by dz, and you have u1, u2, u3. I hope you're not getting confused by the mixed up nomenclature, u1, u2, u3, ux, uy, uc, or uvw, okay? That's partly on purpose and also because I get lazy and I forget what I used last time. And so, but please don't get confused about it. Different professors are going to be using different nomenclature, okay? Excuse me. So what you get is same thing you do for the I. You have du2 by dx minus du1 by dy, I, minus du3 by dx minus du1 by dz, j, plus du2 by dx minus du1 by dy, z. Sorry, k. Okay, sorry, this one should be du3, du3 by d. So for I, sorry, I completely messed this up. For I, you have du3 by dy minus du2 by dz, right? And this one, du3 by dx minus du1. Okay. Now notice one thing here. In the I direction, there is no x derivative. In the j direction, there's no y derivative. And in the z direction, there's no z derivative, okay? So it's kind of taking the components from the plane perpendicular to that direction and doing something to them. But what does this vector measure? curl u, curl of u, is a measure of the rotation of u. In particular, the example that I want to give is, and you can try this next time you go maybe to the aquarium, the Loveland Aquarium in Draper, or any place where you have a channel flow, where you can see water flowing and it's bounded by two boundaries, okay? Really, any even if you go to a creek, but pick a spot where there's like a nice, clean, defined boundary, okay? And buy a popsicle, eat it first, enjoy it, then clean it up and take the stick from the popsicle. So if you take a popsicle stick, okay, and then convert that, cut it in half, and make a cross out of it. Okay, make a cross like this. Now take this cross, eat another popsicle, okay, put one cross in the middle and one cross near the boundary. Okay, can you guess what's going to happen to the cross? Okay, so Sam is saying that which cross is going to, you did this, right? Both will spin? Some. Correct. So this, which one is going to spin faster, which is going to spin slightly lower? Why? Okay. So let's try. You're almost there. Okay. So you would agree that if there's fluid over here, nice and smooth, you could measure the velocity of the flow at every one of those points over here, correct? You can measure the velocity. Okay. Now, if you measure this, and I'm going to give you kind of this answer, what you're going to see is that you're going to see the largest velocity sort of in the middle, and then the velocity starts kind of going down a little bit, going down a little bit. And I'm exaggerating, and it kind of goes all the way to zero over here. Same thing over here. You get this kind of nice, smooth profile. Okay. So at the velocity, we call this the velocity profile. It's going to look like this. Okay. So let me adjust these guys so that they look like I want them to look. Now, put that cross, get another. Okay. So we're going to now take this cross and put it here such that this edge touches this velocity, that edge touches that velocity. You're going to take the other cross and put it over here. Now, which one is going to spin faster? So first, Sam is correct. It's going to spin. Why? You know, answer that. So think of this edge. Think of this edge here and that edge there. The edge at the bottom is moving at a higher speed. The flow is going to move that stick, right? It's going to push, it's going to move at a higher speed than the edge at the top. So it's going to spin it, right? So, you know, this is the stick. Okay, it's going. And then if I push this guy here faster than that guy, it's just going to spin, right? This one is going to spin also. But the difference between the speeds at these two edges over here is lower than the difference between these two speeds. So this guy is going to spin, but much less than the other guy. It's really cool what you'll see. This one is going to start spinning. This guy is just going to barely drift and spin very slowly. Okay. How do you measure that spin? By taking the curl of this velocity vector field. In this case, in this particular case, with this velocity only in this direction, so this velocity over here is simply ui, and it's a function of r squared, okay? Then the curl of u what direction is going to be the curl of u? How many components is going to have? Think about this. The velocity is only in the axial direction. There's no other velocity components. It's one-dimensional, right? It's going only in the x direction. Curl, okay, let's take curl. In the I direction, it's got u3 and u2, which are 0, right? So there's no I direction. So it's going to be 0I. There's no component in the I direction. What about the j direction, the y direction? So if this is I, j, and then k, okay? J direction, you got u3, okay, minus u1. So u3 is 0, but u1 is not 0. However, it's not a function of z. So you get 0j. Kind of froze for a moment here. I forgot that there's last one. u2, there's no u2. Okay. However, there is a u1 and it changes in the y direction, right? u1 changes, the velocity changes in the y direction. So you get minus du1 by dy, okay. That makes sense because this cross is spinning in the z direction, right? The direction of spin, well, the normal vector to the spin is like this, right? So it's pointing in the z direction. So curl u is a measure of rotation in a fluid. Okay, so now we have, I make these two statements that when curl u is equal to 0, absolutely everywhere in the flow, when curl u is 0, what does that mean? There are cases where this could be different, such as the irrotational vortex. It's just, remember, curl u has to be 0, not the velocity has to be constant. There are other answers where curl u equals 0 such that the velocity is not constant. The correct statement to say is curl u equals 0 means the flow has no rotation, or in other words, is irrotational. Potential flow, what you learned in your undergrad. This is the condition for potential flow. Once we derive the full equations, you're going to see that the way this was figured out was like they derived the equations of motion, and then they said, oh, if we get rid of this term, everything is simpler. But getting rid of that term has consequences on the how realistic the flow is. It's still nonetheless a model for fluid mechanics. Professor Hafner was just telling you about ideal gases. Potential flow is the equivalent, is the simplest type of fluid you can deal with. Okay. The other statement is when the divergence of the velocity is equal to 0. We said last time, if flow is converging to a point, then there is divergence. If there's more coming in than leaving, there is divergence. If whatever is coming in is leaving, exactly, we get div u equals 0, then we say the flow is incompressible. And I insist on the flow is incompressible rather than saying the fluid is incompressible. Once we derive the equations, you're going to see why that is the case. Okay. I think I'm almost done. I'm going to give you three more equations that we are going to really need as we continue our derivations. So keep that in mind for the homework. Curl u equals 0, flow is irrotational, and div u equals 0, flow is incompressible, okay? And I called it homework 2 because there used to be a homework 1 where I had you like fill out a survey. So forget about the numbering. You didn't miss a homework 1, okay? I did not assign that at all. So there's no homework 1. I'm gonna start indexing from 2, okay? All right. A couple of integral theorems that are very important. First, we're gonna look at what's called the gradient theorem. I'll explain to you why we need to know of these theorems. The gradient theorem says that if you consider a region in space, a closed region in space, you know, we're gonna like pick a little sphere, maybe, okay, and assume that over that sphere or over that region in space, the entire space, there's a scalar phi, okay, x, y, and z. Okay. Then the theorem says that the integral, the surface integral, I'm gonna put double integrals here to enforce that this is a surface integral. The surface integral of phi n ds is equal to the volume integral over this volume enclosed by the surface of the gradient of phi dv. Phi n ds is simply the flux of phi through the surface, right? You take phi, multiply it by the normal. So n ds is simply this. This is n, and ds is the area on the surface, okay? And n is the unit normal pointing outward. dv is the volume. So dv is in small volume over here, okay? Now this is important because it converts a surface integral to a volume integral. How are we gonna use that? Gonna jump the gun a little bit here to explain to you the setting that we're gonna study fluid mechanics. We're gonna look at fluid mechanics from an integral perspective and from a differential perspective, and those should be consistent with each other. But to jump from, so we're going to derive the integral perspective, which is going to be really easy to derive. We're going to derive the differential perspective using a different approach, but then we should be able to jump directly from the integral to the differential perspective. Okay, so that's the third way we derive the equations of motion. You will notice that in a fluid, there's going to be volume integrals, forces acting on the volume, such as gravity, and forces acting on the surface, such as pressure, okay? Then we're gonna say, okay, the equation in the integral form has got mixed integrals, volume integrals and surface integrals. If I need to jump to do something about that, to take out the integrands and express those as a differential form, I better make sure that all the integrals are of the same type, either volume integrals or either surface integrals. To do that, we need these kinds of theorems. So this is the first one. Specifically for the pressure, what we're going to notice is that in our equations of motion, we're going to get an integral of the pressure. The pressure is a scalar, it's not a force, okay? Only when you define a surface does the pressure become a force. You say the pressure force only on a surface, but the pressure at a point, it's a scalar, it doesn't have a direction. It acts in all directions. There's no force definition for it, okay? We will see that if we use this integral definition, that this becomes grad T dV. And this is going to be the term that you've seen in the Navier-Stokes equations. It comes from this translation, from the surface integral to a volume integral. Everything is going to be in volume integral form. Then we can pull out the integrants and say this is our differential equation. You will see how we will do that later, okay? Now, the divergence theorem. So this is an integral theorem for scalars. There's an integral theorem for vectors called the divergence theorem. or the Gauss Ostrogradsky theorem. Okay, give credit to those great people. It says that the surface integral, we're going to do the same thing. So now rather than having a scalar, we're going to have a vector of u dot n ds. So that's the flux of this vector field is equal to the volume integral of u dv. Okay, divergence theorem. Same thing. We're going to have surface forces expressed as this integral, specifically in the momentum equations, that we're going to want to convert to a volume integral. Okay, and we kind of saw that last time where we defined the flux over a surface. Okay, one little thing you can always do is do a unit check. Okay, so in this case you have meters per second times meters squared, right, ds. And over here you have the gradient is 1 over meter times meter per second times meter cubed. So you get meters cubed per second, meters cubed per second. Okay. There's one last theorem. We're probably never going to use that. I just want to put it out. It's called Stokes Theorem or circulation theorem. This theorem was also known as Green's theorem. For some reason, I forgot that. Okay. It says that so if you take a line or a curve C, and this is a line DC, okay, and there is some flow over here. The flow, you just define a line, so this is flow U, okay. Then this says that the circulation, so integral over this curve C of U DC is equal, this is going to be crazy, the integral over the surface. So here we went from surface to volume. This one is going from line to a surface, okay? Is the integral over the surface of curl U dot N ds. And this is N and ds, okay? I don't think we're ever going to use that, but it's out there for convenience. Okay. I was going to talk a little bit about cylindrical coordinates, but instead I will just give you handouts for the gradient and the curl in cylindrical coordinates. Is just a different coordinate system. In the homework, you're going to have to evaluate the gradient of the pressure in a polar coordinate system, and I give you what that gradient is. And so I'll just write this out here. So I'll give you this kind of information on your exams and your homework, so don't worry about those that much. But in a cylindrical coordinate system, I'm assuming you have some familiarity with that. Coordinates, you know, if vector A, if it's expressed as AX I plus AYJ plus AZK is going to be expressed as AR ER, unit vector in the radial direction, plus A theta E theta plus AZ EZ. Okay, the idea of cylindrical coordinates is that this is z, x, y. Let's see if I can do this correctly. Okay, there you go. Okay, is that at any point in space, x, y, z, you can define another kind of reference. So if these are I, J, K, then at any point in space, you can also define, so if you pick this point, then you define the radial distance to this point, so that gives you the unit vector ER, so that's kind of the radial distance. The height on the Z direction, so that gives you EZ, and how much angle you are away from the x-axis, so you get an E theta over here. The problem with this coordinate system, it does simplify a lot of things. The problem is that as you move in the XYZ plane, ER and E theta are going to change, right? So if I'm over here, then my E and my, let's say this corner is my reference. This is the XYZ plane. If I'm standing over here, then ER is like this and E theta is like that. Then if I move over here, ER points in this direction and E theta points in that direction. Okay? So ER and E theta, they change as you move in the space. That complicates the algebra just a little bit, okay? And you can translate between the two coordinate systems, okay, very easily. With the what's called the similar to the rotation matrix. It's skipping my mind. It's not a rotation matrix, just a coordinate change matrix. So if we take the velocity vector field, which is ux, uy, uz, and that's equal to ur, u theta, uz. Well, they're uz is going to be the same. Okay. What's going to happen is that you can do both of these things. ur, u theta, uz is equal to, we can derive all the math that should have been done in your physics. Sine theta 0, and then minus sine theta cosine theta 0, 0, 0, 1, ux, uy, uz. Oops. So if you had ux, uy, uz to get ur, you just simply multiply this matrix by this vector. So ur is cosine theta ux plus sine theta uy plus 0. U theta is minus sine theta ux plus cosine theta uy, and uz is equal to uz. You can do the same thing if you are going to go from cylindrical to Cartesian. Cosine theta, sine theta 0, showing you it's actually the same matrix. Hold on. Yep, sine theta and 0, and then we have it's the same matrix. Minus sine theta cosine theta 0, then 0, 0, 1, and you are the theta uz. Okay. Same thing, the gradient and the so before going to gradients, A dot B is simply the same AR, BR plus A theta, B theta plus AZ, BZ. And same thing for A cross B. You just do the matrix thing, ER, E theta, EZ, and then AR, A theta, AZ, BR, B theta, BZ. Okay. Finally, the gradient and the curl, they change a little bit because you have derivatives. So gradient in cylindrical is equal to d by dr, 1 over r d by d theta, and d by dz. So this 1 over r, if you think about it, r d theta measures in arc length. And that's what actually accounts for your movement in the plane, okay? And this needs to have units of 1 over length. So this 1 over length, 1 over length. 1 over theta is dimensionless, okay? So that's why you need the 1 over r as well. And the curl of u, and I'll give you all of these equations, okay? All of these things. I do not expect you, I don't waste my disk space up here to memorize these things. D by dr, d by d theta, d by dz, ur, u theta, uz. Okay? And then you just carry that out. Okay. Whew. Okay, we're done. We're done with not with fluid mechanics. We haven't even started in fluid mechanics yet. Okay? Perfect timing. I think we got 20 minutes to get our discussion started. Give you a moment. So again, I'll give you all of these, whatever you need, okay? But you have to know which one to use, right? I promise this is not math hazing. You should have seen when this course was taught with tensors. It was like hours upon hours of just tensor, just, anyway, it was too much math for our purposes. Okay. All right, are you ready for chapter 2? For the second chapter in our course, let me erase all of this. Before I erase, let me ask a question so that we optimize our usage of time. Okay, assume that I am an alien. Okay, I really want you to assume I'm an alien, okay? And like a legitimate alien. And I come here and I bring with me some material, okay? We're gonna call that material fluid. We're gonna call it fluid. Agree on that, okay? We're gonna call it fluid. And because I live in the universe, I'm not gonna tell you where, you know, just for privacy, okay, what planet I live on. I bring fluid with me and I bring it to Earth. And you know, because I live in the universe, said fluid obeys, as far as we know, the same laws of physics here on Earth as it is in the universe. Agreed? We agree on that. And I bring said fluid to you, and I ask you to help me study it. You're all engineers, okay? I want you to come up with a way to try to describe the motion, like what we need, ingredients that we need to describe the motion of said fluid. I assume that you know the basic laws that were derived by the great mathematicians and physicists, you know, such as Newton, Einstein, etc. Okay, so I want you to take a moment and think, what kind of things, what kind of ingredients would we need to be able to try to decipher the motion of said material that we called fluid? Okay, take a moment, work in groups, okay, and just give me ideas, all right, while I erase the board, okay? Some of you are making progress. Most of you are making progress. Don't go in the wrong direction. Okay. Stick to kind of the most basic. Okay. I don't see your group names, but I don't remember your group. Oh, alien. Oh, oh, because you are the alien group now. Maybe you're gonna be the first. I want an idea from each and every group. So, all right. Alien fluid. Alien fluid. How do we study alien fluid? So ideas to study the motion. This is important. The motion or behavior of alien fluid. All right, let's start with ideas.
Maybe we should first define a control volume for the system, and then we thought that maybe the density or the viscosity of the fluid.
Okay, so we don't know what the control volume is yet, because I know you know what it is, but we haven't covered it in class, so I'm not going to assume that. But you're suggesting we analyze or study or find density, viscosity. Okay. Other ideas? You kind of have this. Okay. Okay. Yes. Okay. What if we don't? Okay, great. But I'm assuming we don't know the fluid flow equations. So I don't know what equations you're referring to, right? So let's build on that. So you're saying that we want to study to apply the equations of fluid motion to that fluid, but we don't know those equations. So what I'm after is how can we find those equations? So that's what I'm after. Do you want to build on that? Okay, experiments to do what? Experiments to observe flow. Okay. What else? So what I'm after is ideas to derive the equations that govern fluid. And I named it fluid because we're doing fluid mechanics. So my question to you now, is this going to be helpful in making a prediction? So it's important to know the density and the viscosity, okay? But then what? What am I going to do with that? How can I make a prediction if I put that fluid in a pipe? Or if we put that fluid, and do an ice bucket challenge with it? something like that. So, or you use it. Can we use it to? Can we compress it or not? Right. So how is that? Does that gonna help us? Not that much. It's gonna tell us, yeah, it's viscous, it's got this density. Then what? Experiments. They're gonna give us an idea of how the fluid behaves, but it's not giving us a tool that we can use to make predictions where the fluid is put under different conditions. So how about we think a little bit differently, okay, about this? So what are the great laws of physics in the universe? Before you think about density, viscosity, anything, what are the great laws of physics in the universe? If you're driving your car, you accelerate, what happens to you? Pull back, you push the brakes, pull forward. Okay. If you are driving at steady state, you're not changing your speed, you're not really feeling that you're driving. So what is that law? So Newton's, or how about we say, okay, if this fluid lives in the universe, so it must obey Newton's law, right? So how about that for a way to figure out what this fluid does? Okay. So now, okay, I gave you the first hint. So Newton's second law. What other laws can we think of? This fluid lives in the universe. It needs to obey the great laws of physics. What if you heat the fluid, you add energy to it, subtract energy? What is that law called? Who's taking the course this class? What is Professor Hefner teaching you? Thermodynamics. Yes. Laws of thermodynamics. Dynamics. What do they tell us, the laws of thermodynamics? They tell us about the energy transfer out of that fluid. Okay. More. Okay, what if we observe that, we use a pipe, we spill that fluid in that pipe, whatever goes in goes out. Conservation. Really, all of these laws, they can be summarized into great conservation laws of physics. Conservation of mass, momentum, and energy. Do you see what I'm headed here? We bring this fluid, we want to describe it. What is the toolkit to be able to describe the motion of that fluid? We rely on these great conservation laws. And I want to show you that you actually, now together, you actually know the equations that govern fluid, and therefore the equations that govern fluid mechanics. We're going to do this right now, okay? So let's start with conservation of mass. Conservation of mass. What does conservation of mass tell us? Don't go relativistic on me, okay? We're assuming still kind of low speed mechanics. What does conservation of mass say? Mm-hmm. So in other words, if I put some of that fluid in a bucket and I move it from here over here, what happens to the mass? Doesn't change, okay? So in other words, mass equal constant. Okay. Now, I told you last time that we'd rather deal with rates of change rather than values themselves. Mass equal constant, you're going to have to carry the word constant everywhere and maybe assign a value to it. What's a better way to describe this statement? Okay, so I'm going to take this bucket. I moved it, so, or I put it and I put a timer, assuming, no evaporation. We can account for evaporation, etc. But let's forget about that for a second. What does this statement mean? Tells us, yes, tells us that the mass does not change over time. There's something critical about these laws of physics, is that, we're going to talk about this at the end, is that there's no space in them. It's only time. Okay, it's only time. Okay, what about now conservation of momentum, or Newton's second law? Conservation of momentum. What does Newton's second law tell us? D by dt of mv, or is equal to summation of forces. Right? Newton's law. M is the mass of the fluid, or any blob of that fluid. V is the speed at which it's moving. Summation of forces are the forces applied on the fluid. You will see that the rest of the class is going to be focused on figuring out what these forces are and expressing them in different forms. But just to kind of think a little bit outside the box, what kind of forces can we think of? Gravity, right? So that's the weight of the fluid. That's a force acting. The Earth is exerting this force to pull the fluid in. Okay. Plus, we're going to look at what we call pressure forces. Okay. And then there's going to be something else called viscous forces. Okay. But this is sufficient here. Knowing that this is an equation that governs the fluid, I mean, you all know this. Okay, so next, anytime you're considering a problem, a system, this is where you start. Start with the great conservation laws, mass, momentum, and energy. And then go from there. Start simplifying and dissecting and seeing what's going on. Finally, conservation of energy. Who remembers the first law? Thermodynamics says that the change in internal energy of a system is equal to the heat applied to the system minus work done by the system on the surroundings. Okay. Now, again, this is not useful for our intents and purposes. We want to convert this to a differential equation. Energy could be described as, enthalpy converted to temperature, all of that. So we're just going to call it internal energy. We're going to say that dE by dt, just the rates, is equal to Q dot, or dQ by dt minus dW by dt. Simply just rates of change in time. Okay. Now here's the punchline, and I want you to really think about this and take it with you for the rest of your career, because I don't believe this is emphasized well enough. Okay. So we derived here the equations of, I claim that these are the equations of fluid motion. Absolutely, I'm 100% behind this claim. Okay. Conservation laws apply to fluid mechanics, to fluids. These equations govern the motion of fluid. Next question, are they useful in this form? Are they useful? And why not? And I hope you can stay 2 minutes with me, because that's the punchline I need you to go with today. All the laws of physics the great conservation laws, apply to what's called a system. And a system is a uniquely identifiable group of matter that is always together, not mixed with other matter. So when we look at Newton's laws, they were derived, the laws of mechanics and dynamics, they're derived, you apply them for cars, right? You apply them for, a ball swinging in the air, right? That's an identifiable system. It's unique, it's the same. Anywhere it moves, it's the same system. So that's why it allows you to isolate space. There's no space involved at all because you're just simply tracking how that system moves in the world. So from the perspective of the system, there's no space. All it's feeling is things that change over time. All of these laws apply for systems. For a fluid, the problem for a fluid is, what is the system of the fluid? If you take the entire bucket, they're just going to give you a macroscopic description of that bucket. But what if you're interested in knowing what's inside the bucket? Take the pipe flow. Flow in your veins. I want to know how the blood is behaving close to a little stenosis in my vein. Where you have some cholesterol, accumulating, it's causing some restriction in your vein. You want to know what the velocity looks like over there. So in that case, you cannot take the entire blood of my body and analyze it this way because it's useless. What I want to know the little details everywhere in the flow. What that means is that in a fluid, you have to define hundreds of billions of systems, hundreds of millions of these little systems, okay, and track all of them to use these equations. And that is impossible to do. Maybe one day when we have very large supercomputers, we can do that, but analytically, there's no way we can do that. Even current computing, we cannot do that. So that's the problem with these equations, and specifically these derivatives. And notice the symbol I used, lowercase d, to describe that that's a total derivative on the system. Our objective next time is to start thinking about converting this term into something that we can work with. We call this approach the Lagrangian description of mechanics, where you are tracking systems as they move and evolve. You become in the system, okay, you track it, it only changes over time. What we want is what we're going to call the Eulerian description of fluid motion. We're going to dissect this guy and convert it into something more useful for us. Okay, thank you so much. But keep that in mind. The laws of physics apply to a system, okay, not the way we look at fluid mechanics with partial derivatives, etc. Okay, so there's one more step we need to do. Thank you. A Lagrangian, this is Lagrangian, all Lagrangian.
Lagrangian, we need the Euler.
We need the Eulerian, yes, yes. The Lagrangian is not helpful because, take a pipe flow. How many systems do you define in a pipe flow to track all of them? It's impossible to track. It's absolutely useless. Okay. Don't forget your power supply. Thank you for staying a few more minutes.